So, good morning. My name is Sebastian, and I'm doing a talk about range libraries. And if you check the program, you will see that my talk is called Iterators May Stay there. At some point I changed it. I'm saying iterators will stay. And I know this is a bold statement. And if you want to argue it, please do. I want there to be a lot of discussion during this talk. I'm making some more or less unsubstantiated claims in there. Please argue with me. Do not hesitate to ask questions, to tell me I'm wrong.
Okay, you're wrong. I mean, do you really need to improve this for this audience?
Yes. I don't have enough slides not to. So this morning, I realized I don't have a single funny slide in my talk, so right. What's a range library? Just a short question. Who here was not at Chandler's talk? Jeff. Okay, good. Because Chandler talked about what is a range, which is great. So because this means I don't have to talk about that. I can just talk about what is a range library. And a range library is essentially, we want to do this. We don't want to do sort v.begin, v.end. We want to do sort v. And we want equal range to return something that we can directly pass on to another algorithm to copy. Right? And unless you're Chandler, because then you want to do v equals sort move v. This is also something we generally want to do in a range library. We want this thing called adapters. So this is kind of lazy, right? So I've got this vector of integers, and I want to filter it, only get those that are even, and then transform it so that those are divided by 2, and then iterate over the result or pass the result to an algorithm. And we want that to be lazy. So it shouldn't need additional storage at the beginning to put that there. We just want to say, well, if there's a non-even thing, then skip it and calculate that on the fly as you iterate. You can do that with iterators. It's annoying. I have a slide later about that. Right, so adapters are wrappers for iterators or ranges. And what they do is they modify the primitive operations, right? So if I have this filter adapter here, if I increment, that thing checks, well, does the new element match the predicate? Does the predicate return true? If not, it just skips over it. So we modify the increment operation. And the transformed adapter that we had there modifies the dereference operation of an iterator, or whatever the equivalent is for a range. So there's the standard committee created the study group 9 for ranges, because the standard committee does want some kind of ranges in the standard. It was established late 2009, early 2010. No, your mail to the SG9 mailing list is from January 2010. So, and in this, Marshall heads this group, and in his initial mail to the mailing list, he said this, or was it 2012? I might have confused that. It might be late 2011, early 2012. That actually makes a lot more sense, because it did not happen before the C++. Sorry, so that's a typo.
Welcome everyone with January 2nd, 2013.
13. Oh wow, bad typo. Sorry.
I was going to say, wait, I've been doing this for 5 years.
Yeah,
No.
I have no idea why I did that. I have absolutely no idea. Okay.
Almost a year and a half.
And in his welcome mail, he said this: the goal of this study group is to research the idea of adding ranges to future version of the C++ standard library and to create a proposal for the committee to consider. And in the time since, and partially before, a lot of people have created their own range libraries, doing what they think ranges should look like. And I want to show a little bit of that work and to compare it. So what's the goal of a range library? A range library will generally have these 4 goals in some measure. We want it to be convenient, because that's the point. We don't want to write sort v.begin, v.end. We want to write sort v. That's convenience. That's the reason why we want this. We still want to be efficient, right? This is the C++ standard library. We all know if that code doesn't match the handwritten code, people will complain. And it should be no different for a range library, right? We want it to be safe to use. We know that's not always possible, but it's a design goal to consider. And if possible, we want to reuse our existing code that uses the STL or is written in consideration of what the STL looks now. So let's look at these goals in detail. Reuse of old code. I'm going to talk about that first. There's 2 things to that. We want to use standard iterators, as we get them from the standard library now, with algorithms that are written for our range library. This is pretty easy to achieve usually. You can usually just take 2 iterators, make a range out of them, done. I haven't seen any place where it doesn't work. We want to use ranges that we define in all algorithms. So we want maybe to take that range, get a begin and end iterator from it, and then use it with all algorithms, or just a for range loop, right? This is much harder. If you want that goal, you're really restricted in what you can do. And I'm going to talk about that later. Nevertheless, if we want something in a standard, it probably will have to have pretty good compatibility with old code. We probably do not want to have ranges in the standard and they're disconnected from the iterators, so that if a new component is added to the standard and it only provides ranges, suddenly you can't use any code you've written, any algorithms that use iterators for it. That's probably a non-starter. So this is an important design goal if you want your library to be standardized. If not, who cares? Convenience. As I said, this is the reason we want ranges, right? We want the lower line, not the upper line. And here's the other line that I had in my introduction slide. With ranges, it might look like this. Without ranges, in the current standard library, you call equal range. It actually returns a pair, so that won't actually work. But let's assume it returns a std iterator range that has begin and end member functions, and it's these 2 lines. And it doesn't compose. I cannot take the result of equal range and pass it to copy. So this is really what we need. Another point in convenience is a claim that I make is that iterators are hard to write. This is from Eric's blog post about his range library. From the first post, he wrote a C string, a null terminated string range, and it provides classical iterators. And this is the equal function for those iterators, right? So when are 2 iterators equal? Well, the C string iterator, a C string has a sentinel at the end. So you cannot say, well, give me iterator for the end of the string. You don't know where that is. You'd have to do a linear scan over the string first. So an end iterator, there is a sentinel, and it's marked by simply having its internal string pointer being null. So when you compare two iterators, they might both be null. They might both point to somewhere, or one of them may be null. And this is the code to consider that. And I'm claiming that if you don't use iterators, or if you use something else than our current iterators, this is easier. Like Eric wrote in his blog post, if the sentinel at the end doesn't need to be the same type, if it can be something special, then this becomes much easier to write. Adapters. Iterator adapters are hard to use. Who here has used the Boost iterator library? A lot of people, right? Does that look familiar? And I'm not even using filter iterators here. With filter iterators, it's even more annoying. If you have a range, then it's one call. It's not, well, there's one iterator and I have to wrap it, and another iterator that I have to wrap. No, I've got one range, I wrap it, and I wrap that. Done. And the third claim I'm making is that adapters for iterators are hard to write. So adapters are sometimes hard to write even for ranges, but I've written a filter iterator, and once you get how it works, it's not that complicated, but it's not easy. You have to realize that when you increment the iterator, you might actually go past the end of the range. So you need to store the end iterator in your iterator adapter to make sure you don't go past that. And then you realize, well, what if the iterator that I get passed into the constructor of my adapter points to an invalid element, to one that should be filtered out? So I need at construction time already advance, unless it's already the end. So it's very easy when writing an iterator adapter to accidentally not consider some case, add undefined behavior, and don't try to write a concat iterator. Don't even try. Next goal, efficiency. If we want to write a range library, the hard goal is we need to be at least as efficient as the current STL. That's achievable. That's doable. And like the STL, we want minimal overhead over handwritten algorithms. That's a little harder because the STL is not perfect either. On the other hand, as Eric showed in his blog posts, in some cases the iterator abstraction is actually problematic, and a different abstraction is easier and gets more efficient code. Like the C string range that he wrote with classical iterators generated horrible code just for string length. And if you replace the end by a proper sentinel iterator, or if you use a range abstraction, the generated code is much better. Aside from runtime efficiency, there's also the space efficiency problem when you write adapters. A protection iterator, like the transformed, means that every iterator stores the function object that is used to transform the value. If that's a stateful function object, that means that for a range you'd store that object twice. If you have a filter iterator adapter, then that filter iterator has both the begin and the end of the underlying range. so it's twice as big. If you have 2 filter iterators, well, you have 4 underlying iterators. If you then filter those again, you duplicate the space again. So if you stack adapters that need to know the end position, you get exponential explosion in space requirements. And iterators are just a few bytes. Who cares if it's 4 bytes or 32 bytes? Well, you pass iterators around a lot. And when you call functions, it's very relevant whether that thing fits into a register or not. Which brings me, yes? Yes? So, absolutely. Eric said, well, if you do a projection iterator, and as the projection function use a lambda, you might capture arbitrary state in that lambda, and every time you copy that iterator, you copy all the state along with it. Which is a problem that is not just limited to iterators. That problem can be avoided if your ranges are not copied around a lot too. Depends on how you implement ranges. We'll see that much later. So anyway, that brings me to an efficiency issue that you get with ranges, because I'm not here to just say iterators are bad, use ranges. I don't want to do that. Andrei Alexandrescu did that. He had a keynote. It was called Iterators Must Go. By the way, I should have maybe mentioned that earlier. Well, it was in this room. It was right here. He was standing right here and said, don't use iterators. I'm not here to do that. I'm here to compare the approaches. And ranges are not all sunshine and daisies. If you have ranges, you need a good calling convention, because if you have a vector range, that range is going to consist of 2 pointers. If you have a function that takes 2 iterators, 2 vector iterators, that function takes 2 pointers. That's 2 registers, right? That function will, in any modern calling convention, put the 2 iterators into registers and you're fine. If that's a range, then that's too big for 1 register. So you're going to pass it on the stack, unless your compiler is smart enough to say, well, that's a trivial thing. I'm just going to split it up, put it in 2 registers. In D, they actually went to a lot of effort to make sure that happens, because D's standard library uses ranges in the library. Right? This is one of the libraries I'm going to look at later. And finally, we get to safety. We want to, without sacrificing performance, be as safe as possible. We want to detect out-of-bounds accesses if possible. If I have 1 iterator and I increment it, do I know whether that's safe? Well, maybe. Depends on the underlying structure. If it's a vector iterator, I don't. It's just a pointer. I incremented it might point to the vector or not. If I have 2 iterators, I can say, well, yeah, those are now equal. I can increment it further, but it's an increment operation. I only have 1 iterator. A range, if the range is there, the range knows whether you can still increment the beginning. So that makes ranges a little safer there. And the other thing that happens with both iterators and ranges, they get invalidated. If the vector goes away, all iterators to it, all ranges on it, they're invalidated. And without really complicated debug tricks, you cannot detect it. So that's an issue we always have to be aware of. we want to avoid making it worse. We want to avoid designing in our library that suddenly something gets invalidated, although we didn't expect that. So here are the libraries I'm going to talk about. Yes? I'm not sure if I understood that. So the yes. Mm-hmm. Mm-hmm. Okay, so if I understand it correctly, you say that an efficiency goal is that if we have a range, we wrap it in an adapter, we wrap it in another adapter, that should be as efficient as if we had written a special adapter that does the operations of those two adapters at the same time. Yes, that's nice to have. I think you're pretty much, unless you really screw up the interface to your library, you're pretty much dependent on the compiler to inline stuff there to achieve that. So don't screw up the interface. Okay, so I'm gonna look in a little more depth at a few libraries. There's Boost Range 2.0. It's been in Boost for quite a few years. The second library is Eric's Range v3, which he talked about in his blog posts and which can be found on GitHub. Then I'm going to talk about Andrei Alexandrescu's Stud Range library, which is in Phobos, the D standard library. It's basically from his Iterators Must Go talk, the ideas implemented in D. And the last library is libaccent, which I wrote. And it's kind of like Andrei's library with some modifications, and also it's written in C++. So there's the big divide here between those libraries, right? Boost Range and Eric's Range, they use iterators still. They provide iterators. In Eric's case, they don't provide completely classical iterators. Whereas Stud Range and libaccent, they don't have iterators. There, the range is the primitive. In the above two, a range provides iterators that you then use to actually access the elements. In the lower two, the range itself provides the elements. Any questions? Good. Boost Range. Anything that you can call boost begin and boost end on is a range. And it's got to return an iterator. It's got to return a normal standard iterator. Which means it's absolutely perfect compatibility with the standard. You take two iterators, you wrap them in an iterator range, you've got a boost range. If you have got a boost range, you call begin and end on it, you got two iterators, you can use them in old code. This is great. Unfortunately, it means it inherits all the efficiency and safety downsides of both ranges and iterators. So, because the actual iteration still happens with iterators, an iterator cannot detect out-of-bounds access, for example. And it also inherits some of the convenience downsides of iterators and ranges, specifically not when using them, but when writing your own adapters, for example. So anything with begin and end. A vector is a range. a stud pair, at least in early versions of boost range, was a range, because boost begin and boost end worked with that. A range doesn't have anything beside those two functions. Everything else is implemented by getting the iterators and working with those. So the iterator is still the main primitive. And here's how boost range implements its own version of sort. It takes a range. So it calls boost begin and end. It passes it on to std sort. I believe it has overloads for both const and non-const. It has to accept it by non-const because a vector is a range. And if it takes a const ref to a vector, then sort won't work. Right, the question was, does boost range really accept a non-const reference? It inherits the efficiency and safety downsides, right? It has no protection beyond what iterators have. Some range libraries know when they're empty, and if you then try to access the next element, they can assert. Boost range depends on the iterators, and the iterators, well, there's the debug standard libraries. Has any one of you ever written their own iterator that had debug and a debug interface? Except Howard? Eric? Great. Oh, 3 people actually. I'm surprised. Yes, true. It's not easy. Because adapters work at the iterator level too. Because if you write in boost range, if you write an adapter, well, that's a new range, but in the end it has to return iterators. So you have to write the iterator adapter. And that means you still get the space explosion problem of filter iterator. And still, the range is still a big object. So although it uses iterators, at some point you're still passing ranges around and they're big. So it still depends on the compiler to split the object up. Except that ranges in boost range are usually passed by reference. So that point doesn't really apply, but. And as I said, if you want to write an adapter, you have to write an iterator adapter. And I still claim they're harder to write than range adapters. All right. Any questions about boost range? Okay. Eric's library is, the fundamental idea is that, well, 2 iterators are not always a very good way of expressing a range, especially when that range is terminated by some kind of sentinel, or if the iterator refers to some sequence that knows when it's empty, like a stream, right? So what Eric said, well, what if we say that the second iterator, that the end iterator does not have to be the same type as the first? Well, that's a bad organization here. If the second iterator can be a different type, then we can implement equality to mean something different, to mean something special. And that makes it easier to write iterators for some kinds of ranges, especially sentinel terminated ranges. And so he created this new concept called iteratable, which is like a range, kind of like a boost range, in that it gives you a begin and an end iterator, but they don't need to be the same type. The end iterator might be something different. And in his library, a range is basically an iterable that actually does return the same type for begin and end. Did I get that right so far?
Yeah. So another way of saying that is the range concept is a refinement of the
Yes, the range concept is a refinement of the iterable concept with the additional requirement that begin and end return the same type. So, what does that mean? If you take in the standard library an iStream iterator, that iterator has a reference to the underlying stream. That stream knows when it's empty. Therefore, the one iterator knows when it's empty. What's the point of having an end iterator that says, well, here is where the range ends? That's not meaningful. And because it's not meaningful, it's ugly to implement. Because in the end, it means, well, the iterator then has not only a reference to a stream, but it also has a flag that says, I am the end iterator. And when you compare that to a normal iterator, well, if you compare two of these iterators, you have to say, well, this one does not have that flag set and this one has. So, well, I guess a call is done on this one. But if they have both this flag set, then, well, they're return true. It's more complicated than it needs to be. What really should be, well, are you done? Yes. Great. I don't need anything else. Actually, this is an input iterator, right? So comparing two iterators does not even make sense. Because the way input iterators work is you copy, if you create a copy of an input iterator, and if it's not a copy, if you have two input iterators that refer to completely different streams, comparing them is undefined behavior, right? Generally, you cannot compare iterators to different underlying sequences. So it's only meaningful to compare two iterators when they come from the same range. So how do you get input iStream iterators? Well, you create them from a stream, or you create the end sentinel iterator. And two iterators from the same stream, well, either you just created them both and they're equal, or you incremented one of them and invalidated the other with it, because that's what input iterators do. You increment one, all the copies get invalidated. So the only useful thing you can do with equality is comparing to end. So why not call is done? And if that end sentinel iterator is a different type, then we can overload equality so that comparing to the sentinel iterator just means is done. And that's efficient. And it's easy to write. And then the equality between two iStream iterators is just return true. Because either they're equal or the equality operation is undefined in the first place.
And you might as well return true.
Yes. Yes, exactly.
No wrong answers, right?
Exactly. There are no wrong answers. True can never be the wrong answer. Either it's the correct answer or it's undefined behavior. You're not limited to just saying, well, that's an AND sentinel, so I'm going to ask that iterator whether it's done. I can actually represent an arbitrary predicate with that. I can create an iterator sentinel that I compare to any other iterator type, and when I compare it, it says, well, give me the value at that iterator and check it against the predicate. And if the predicate returns true, I'm saying, well, we're equal. So I can cut it. I can say, well, I have a vector iterator, and I want to iterate until it encounters 42. I can create a custom AND sentinel that says, well, dereference that other iterator. If it's 42, then we're equal. Yes, Jeff?
So why do they have to be a separate type? It seems to me you can have an sentinel type that just, well, it doesn't need to be a separate type. You can change type. You can create still call it that. Still makes sense.
Why do the iterators have to be the same type? They don't have to be.
Well,
The
I'm saying, why do they have to be different types to make the behavior that you're
Eric?
You don't have to be different types to get the correct behavior. You can implement it, it's been implemented. I've seen iterators one or two things. It's hard to implement and it generates terrible code and runs slower. That's why. Yeah, so you make the internal iterator as a variant, either a rule or as a point. And so the N1 is the
That's still a flag.
then it's going to be slow. But the comparison is just, oh, if I got, you're saying variant is inherent. Sure.
So yes, so to sum up this discussion, Jeff asked, why do they have to be different types? Well, you could just make one iterator that's a variant of the normal iterator and the end sentinel. And the problem with that is it's slow, because comparison then has to check, well, which one is that? It has to do, effectively, it has to do dynamic type dispatching of some kind. And actually, it's not only been done in the standard library, it's actually been done in Eric's library, because he has a special adapter that transform an iterable, where begin and end are different types, into a range where they're the same type, exactly by doing that. Right? Exactly by having an iterator adapter that is a variant of the two things. Which makes it slower and bigger, because now the variant has to store the tag, type tag. Yes? Yes. So
Well, that's a very interesting kind of range. That's an infinite range, and there are all kinds of different ranges. I will take you the report that compares always full. You notice the state that this is an infinite range. But after the case, this different. Checking is I am able to reach the value 44. The range is particular. Otherwise, we will need from this range, but
okay, so to sum that up, the objection was that the example I brought of that special end sentinel that just checks the predicate. What if the predicate never returns true? And if the iterator, the iterator that you actually increment is not really infinite, but it never encounters, like, let's say 42. It's a vector iterator, but the vector does not contain value 42, then it's not safe, because you will run off the end. True? It's not safe. I'm just saying it's possible, and it's an interesting idea. And in the end, a null-terminated string relies on that. So if it's exactly that, except that the predicate is the character 0. And yes, so the string, so the C-style string requires that there be a terminator at the end. Well, maybe the data you have requires that there be a 42 in there. Maybe it's a kind of byte code, and that byte code requires that it ends with a exit instruction. For example, right? So yes, it's not safe in the general case, but it is an interesting thing. And that is a second answer to Jeff's question too, because if they're the same type, it's not extensible, because that predicate iterator that I just said, I can do that for any kind of iterator. It doesn't matter. That iterator doesn't have to know about that idea. I can implement it on my own, independently of anything Eric has done. So, here's the thing though. Once you get to bidirectional ranges, you will probably want to decrement the AND iterator at some point. Eric?
That's not actually true.
Okay.
There's the bullet points only works up to forward ranges and bidirectional ranges. So there's plenty of algorithms which require bidirectional iterators, but that don't ever decrement n iterators. So for instance, like a backtracking regular expression engine would do that. So you should be able to, say, call a regular expression match on a C-style string without having to scan all the way to the end first to find the null terminator. You don't need to know where the end is.
Okay, so Eric basically told me I'm wrong. And he's probably right. And he was very polite about it, yes. So it's useful to have an iterator that can walk both forward and back, for example, a backtracking algorithm like a regex engine. And you don't ever need to decrement the end iterator. Okay, so basically there are some algorithms that are fine with that. Others, like reverse, are definitely not. They need to decrement the end iterator. So it just means you need finer grained distinctions for your algorithms. The other thing that has come up that Sean Parent always mentions is, well, there are some algorithms, or in some situations you don't have two iterators, you have an iterator and a count. And algorithms, to be efficient, often need a different implementation for that case than for the two iterator case. And the question is, can we use these sentinels to represent that kind of counted range efficiently? And I'm not sure if that question has been answered yet. I think there's been quite a bit of discussion. The gist of it that I got is that probably not. It seems that it's not that easy.
I think the answer is yes. I'm working on it.
Eric thinks the answer is yes and is working on it. We will see.
No, I haven't done that.
Okay. So, when it comes to such range libraries, we get lifetime issues, right? Invalidation. Is this code valid? And by the way, that should, in theory, compile with both boost range and Eric's range, unless maybe the adapters are called something else and have different argument orders. Is it safe? Does anyone who has used boost range know whether that's safe? Yes, David says his guess is it would be no, or it wouldn't be on the slide. Well, I have two libraries. Eric, is it safe in yours? No, it's not safe in Eric's library. In boost range, I have no idea. Boost range doesn't document that. Boost range doesn't say, well, if you have an adapter and then you take an iterator from that, does that iterator, is that still valid once the range goes away? For that matter, it doesn't even document whether, well, if I have this transform adapter and then I wrap it in a reverse adapter and capture that, once the temporary transform adapter goes away, is that adapter we captured still valid? I don't know. It doesn't document it. And even if it is, well, if we get an iterator here and then return it and that thing goes away, is the iterator still valid? I don't know. Well, actually, I do. I looked into the implementation. Yes, it is. It's actually valid, because transform grabs two iterators from this vector and creates transform iterators and stores those. Reverse takes those transform iterators and creates reverse iterators and stores those. And the iterators are held by value. So yes, it's safe. Happens to be. I wouldn't rely on it. And then when you return those iterators, well, they're returned by value and they just reference that vector and that was passed in by reference. So it will probably live outside unless you pass the temporary vector to the function, which is your own fault. This function as it is safe in boost range. You just shouldn't rely on it. In Eric's library, though, no. Because in Eric's library, an iterator references the range it was taken from. So when the range goes away, the iterator is invalid. It's a design choice. It's a good thing in some regards, because that means the transform iterator doesn't have to carry around the projection function. The projection function is stored in the range. The iterator references the range and can just use that. And when the iterator gets copied, it copies the reference to the range. Great. It also means that the iterator probably has a better chance at checking whether it's still valid than if it's standalone. But it means this code is not valid. It's a trade-off, right? So iterator pairs can be very awkward. If you have an algorithm that returns a pair of iterators, you can't just pass the result to a different algorithm that expects a pair of iterators. We have the efficiency issues. We have the adapter issues. Eric's library makes it better. It doesn't make it perfect. I don't think there is a perfect way to do this. And Andre's solution to the whole thing was, iterators must go. Throw them away. Do something completely different. And what he said is basically, well, let's make the range the primitive thing that we pass around, the thing that gives us the values, right? So what he did was he has ranges, and you can take an element, you can make them smaller. What you cannot do with a range is make it bigger. Once you make a range smaller, once you chop off elements, you cannot add them back, because that would be unsafe. And safety was an important design goal for him, because you don't know whether there is something else there. You know when you're empty. And then if you then say chop off the first, it says no. But that way, no idea. So bidirectional iterators are strictly more powerful. The backtracking algorithm that Eric mentioned, that's not possible there. You have to actually store copies of the range to preserve them if you want to backtrack. How? Marshall.
I think that the example of this that most people are familiar with, well, many people are trained to be familiar with, is string graph. It implements an awful lot of this.
String ref is a good example of something like this, yes. String ref references a string. And well, you can say substring, and it gives you a string ref that returns to a subset, that refers to a subset of that string. What you cannot do is, if you have a string ref, get a string ref that refers to more of the underlying string. And that's a safety feature, right? So Andre implemented a big library in D. The Phobos stud range and stud algorithm libraries, very complete, and he can do everything. Everything the C++ standard library does, his library does as well, except there's some very unintuitive interfaces there. Like stud find, what does it return? Stud find returns an iterator that points to the element that we found. So depending on what we want to do we want to say, well, I just want that element, or maybe I want that element and everything afterwards, or maybe I want up to that element. You can do all that. If you just have a range, in Andre's library there is no way to denote a position. Find has to return a range. What range does find return? And what if I don't want that range? What if I want another range? Question? You could have a take while and a drop while function, yes, and that's exactly what Andre is doing. So I'll get to that in a moment. just let me go over the range operations that exist. So the simplest range just is forward traversal. It has 3 operations. Is it empty? Get me the first element of the range. Drop the first element of the range. And that's completely isomorphic to a forward iterator. Compare it to the end iterator, dereference it, increment it. That's all there is. A bidirectional range adds 2 primitives. You can access it from the other end. So you can access the last element and drop the last element, in addition to accessing the first element. You still cannot add to the front. You cannot backtrack. And there's random access traversal, which basically means drop arbitrary number of elements on either side in constant time. And yes, there's more functions that you can build on that are useful as primitives, like indexing. But that's pretty much it. Size. Actually, in Andrew's library, size is, so it's not a linear progression, because size is to the side. You can have ranges that you know the size of, even if they're not bidirectional. So yes, size is another operation. Okay, let's go back to find. What does it return? Well, as Michael said, sorry, what's the question? It returns a range, yes. What range does it return? Find returns the range from the found element to the end of the range. So it's basically drop until. Until the predicate returns true, or until we find that element, drop from the front, and then return whatever is remaining. What if I want the range after the element? Well, there's this little convenience function called find skip, and it returns basically the same thing, only it calls drop front one more time, unless the range is already empty. So it basically encapsulates a call to find plus an if plus a drop front. Then there's find split, which returns 3 ranges. It returns a triple of ranges. It returns, well, everything until the found element, then a range consisting only of the found element, and the range consisting of what comes after. And there's until, which actually returns a range adapter that iterates until it finds that element. And you give it a flag to specify whether you want that element included or not. And by the way, find split has 2 variants that just return 2 ranges, where one returns until before that element plus everything from that element, and one returns until including that element and everything after element. So find has become 4, 7, depending on how you want to count them, algorithms. Is there a question, or? We have find and find if. Yes, we only have 2, and they're actually the same thing, because you can always use equals value as a predicate to find if. Right. So that is the reason why I created my library. Phobos style range plus an additional primitive that represents a position. A position is a pretty simple thing. It knows whether it refers to something or nothing. It can be dereferenced to access the thing it refers to. It can be used to cut ranges short. You can take a range and say, well, I have a range, I have a position somewhere within that range. I can say, well, give me the range from that position. What it cannot do, a position cannot move. A position doesn't need to know where the ends of its range are, because, well, it can't move. If you want something else, you need the underlying range. And that means that find can return a position, and that's pretty nice. So find, my find if is called find, because this is easy. It returns a position. And the position knows whether it refers to something. So if find doesn't find anything, it returns a position that doesn't refer to anything, which converts to false. I can write this. How many C++ programmers have used setFind and wanted to write this and couldn't? I can dereference the position and get the element that was found. I can say, well, cut that range off at this position, or cut it off before, give me the part from that position. Question?
What's it returning here? That auto, is that another range?
The auto before and auto after? Depends on the underlying range. So the question is, what do until and after return? It depends on the range. After returns the same type as range, always. It creates a copy set, tells it, well, start here. It's undefined behavior if you try to cut a range short with a position that is not within that range, right? The position is not local to the range, and it depends. Yes, and if the range goes away, the position is not invalidated. And until, if you have a bidirectional range, you can cut the end short. A forward range cannot do that, so in that case, it returns an adapter that basically says, well, is the first position, so I have this end position and I have the forward range, I increment it, well, is the first position of my range now that position, that cutoff position? In that case, I'm saying I'm empty. Question?
So does this mean that your range has a primitive that says get the position of the first element?
Yes. So starting from forward ranges, it has my range has a primitive called give me the position that refers to my first element, and that's actually the only way to obtain positions. Right. So this is my library. This is the underlying idea. What are the lifetime issues of a range library? Well, ranges are always passed around by value. In both Andre's and my library, a range is passed around by value. A container is not a range. So there is actually a function that you need to call to get a range from a container. So you cannot actually say sort vector, or you can only do that if we can recognize, well, that's a container. Let me get the range and forward to the real algorithm, which is possible to implement. It would be a lot easier to implement if we had concepts. When the ranges are passed around by value, that frees us from all the lifetime issues of ranges. The ranges get invalidated if the underlying container goes away, but not if some other range goes away, because an adapter always copies the inner range into itself. Of course, that means that we get some efficiency issues back, because what Eric said, well, if you have the range and then you get an iterator, and the iterator refers to that range, the range can hold the projection function, and it doesn't need to be copied around a lot. If the projection range is the primitive and gets copied around, well, you've copied the projection function. So that's a potential efficiency downside. My positions do not depend on the ranges, which means I can pass in a range by value to a function, get a position back, and use that position on copies, with copies of the range. And that's important. If that didn't work that way, my library would be pretty much unusable. So invalidation only happens if the underlying sequence goes away, if the container gets destroyed. Yes?
Does the previous fee function for your comparative arc library,
Yes?
does that work with your ranges? Would you return a position?
If I return a position, yes. Yes, it does. So the question was in the first lifetime issue slide, where I compared boost range and Eric's range, I wrapped these adapters and then return an iterator. If I return the position there, yes, that would be valid in my library. But I could only dereference the resulting position because I don't have the range. Yes. But I could just reform the range, and depending on what the adapters say, what does the underlying sequence mean? Because my concepts are pretty explicit about what is an underlying sequence. And if the adapter says, well, if you create two transform iterators with the same function, two transform ranges with the same function, then that's the same underlying range, so the position from one can be used with the other. Then you can just reconstruct the range, use the position. Or you could unwrap the position to get the underlying position for a vector range.
It seems to me that to do that, your transform function has to depend solely on the parameter that's passed into it, not any global stability.
To do that, the transform function must, yes, the transform function must be a pure function. If it's not, those guarantees are not fulfilled. And please don't do anything else. whether it's my library or Eric's library or boost range or a boost iterator, transform iterator, please don't pass in a transform function that is not pure. Just don't. So, ranges are only invalidated if the underlying sequence goes away. And if you're using the Phobos stood range, that underlying container is probably garbage collected, so it's not going away. Pretty cool. So, Marshall.
You said you're going to invalidate it if the container goes away. What if the container gets changed?
Good point. What if the container gets changed? Well, it depends on what kind of change. If a vector reallocates, the range is dead, probably, depending on how you implement it. You could implement a vector range with a reference to the vector plus an iterator, plus an index. But then it gets invalidated if the vector gets moved, which the other way of implementing it doesn't. So it's a trade-off. So yes, actually, I have in the comparison that comes now, I have a point about invalidation for ranges, which it took me a long time to discover, which is very interesting. I'll be there in a moment. So, ranges are more flexible in their implementation than iterator pairs. I make this claim that a range, because it's opaque, it just says, well, am I empty? Drop the first element, get me the first element. That means you can hide things like, is it a delimited range? Is it a kind of two positions range? Is it a counted range? Is it an infinite range? If it's counted range, it probably has the additional ability to say, well, I have this many elements in constant time, which is a different concept that it provides, which you can dispatch to an optimized algorithm implementation. With an iterator pair, well, you have to take the iterator pair and say, well, they fulfill together a concept. They have a binary concept that says distance between those is constant time. You can dispatch on that, but it's more complicated. Iterators are more flexible for algorithms. So if you have two iterators, that's a range. If you have three iterators, that's three ranges. From the first to the last, from the first to the middle, from the middle to the last. Range plus the result of find. Right? And an iterator and a count is also a range. Yes. So Andre's range library does not have that kind of flexibility. If you have 4 iterators, if you call equal range, it gives you 2 iterators back. You have 6 ranges. You have 1, 2, 3, 4 iterators. You have 1, 2, 3, 4, 5, 6 ranges that you can form out of them. So this is one thing that I tried to solve with my position, but I added complexity to do it. Ranges are safer. A range knows when it's empty because it has a primitive that says, am I empty? And you can always, in your drop front, you can always just say, assert not empty. If you have iterators, well, you can put in a reference back to the underlying range. Then it can query whether it's where in that range it is. But that means space overhead. And if you don't do it carefully, it means breaking ABI in your debug mode. So you probably want to have some out-of-band data, a hash table that you can look up the iterator in to find the underlying range. Very complicated. And because a range can never grow, well, you cannot run off the other end of the range. So ranges are safer. They sacrifice some power for that, or at least some convenience in implementing algorithms. Because it now means that when you backtrack, you cannot just, well, okay, went too far, go back. No, you have to store a place, go further, and then, oops, return to that, which means space overhead. I claim that it is easier to write range adapters than iterator adapters. I have absolutely no substantiation here in my slides for that claim. You can believe me or not. But I'm willing to listen to any arguments that I'm wrong. It probably is not a good thing while I'm here because you'd probably have to look at code for that. Iterators are harder to invalidate. That comes back to what I said to Marshall. Here's a funny thing. If you do have a list, if you have a std list and you do a splice, that does not invalidate iterators. Iterators stay valid because they refer to one element. And if that element is now in a different list, the iterator does not care. If you have a range and you splice, and the range refers to this list, and then you splice the list and put half that list into another list, suddenly one end of the range is in this list and the other end is in this list. That cannot possibly work. You can no longer reach one end of the range from the other. So what Nat said is that, well, if you have a pair of iterators, you have to be careful too, which is true. But you can still, but if you know what you're doing, you can still use those iterators. The range is dead. You cannot recover it. It's invalidated. No chance of doing anything further with it. Throw it away. The same thing that came up for me when I thought, well, if I have a std list and I want to write a range, yes?
So in your library,
Yes.
if you have a range, you do a splice, you can get the position with the beginning and the end,
And we just,
substitute the ranges from the other two, and then get the positions to create use the positions to create the ranges again.
So in my library, if I have a range over a std list and I splice it, I could still get the positions, front position and back position from that range, and then get new ranges from the new lists and work with those positions. Yes, in theory, you can do that given what the implementation looks like. I would still call it undefined. I would still say a splice invalidates the range and don't use it anymore. You could say, well, if I have a position to that list, the splice doesn't invalidate the position. That's cool. All right. The second point in invalidation is when I thought about, okay, what does a range for std list, what does that do? Okay, it's a bidirectional range, right? It can walk in from both ends. Does it hold account? Does it know how big it is? Because, well, a std list knows how big it is. Whether that's a good thing or not is up for debate, but it does. So, well, when it constructs the range, it could just pass the count along. And if you chop off one element of the list, well, of the range, well, you decrement that count, you keep it up to date. Perfect. And if you do that, and then you take your list and remove an element of that list in the middle, your range has the wrong count. Because the range thinks there's 5 elements in there, but you removed 1. And now the range will be empty and still think it has 1 element left. So if your range over the std list holds the count, it gets invalidated by arbitrary insertions and removals in the list. That's probably a bad thing. We kind of like the fact that std list preserves iterators right now. We probably want that for ranges too. So that's a trade-off again. Do I want that count in there or don't I? Well, the simplest thing is to say, no, I don't, because I can always just wrap that range and tell it, well, this is how big you are. Get a wrapper back that knows how big it is, and then I'm responsible for, well, if I lie to it, it's my fault. You were first. So the question was essentially the inversion of the previous question. So if I have the range that gets spliced in half, well, I could then get a position from one of the new lists and cut that range off so that all of what remains of the range is in one list. Again, yes. Again, that's complicated. I don't want to try to specify that, right? Because in the end, I want my documentation to say when is a range invalidated. And I don't want to have to write down, well, if you splice, then that range is kind of in this weird state where if you do this, that's safe. And if you do this, that's safe. But no, it's invalidated. Don't use it. Eric.
It solves size problem. So when you create a range out of a std list, the range is the list.
If I can solve the size problem by, if I create a range from a list, I can just hold a pointer back to the list. Well, that has some problems. First, if I move the list, the range gets invalidated because it points to the old place. Second problem. Now I don't not only do I have to hold a pointer to the list, but I also have to hold account of how many elements did I already chop off, because I have to subtract that from the size of the list. And that doesn't work because if I have a list, and let's pretend it's just a sequence, right? And I have a range to all of it. Well, if it holds the pointer back to the list, the size is fine. Now I chop off one element of that range. So I remember, okay, I chopped off one element. So my size is the list size minus 1. And now I actually really chop off the first element of that list. Now the list size is as big as the range, but the range still thinks it's 1 smaller. So no, that doesn't work. I think I thought about that too, but yeah. Anything else? We've got 10 minutes left. That's not much, but I think it should. Oh, Jeff.
So, looking at that, it doesn't appear that you've implemented any
You have looked at the repository?
Yes.
So first thing, if you look at the if you Google libaccent, you will find a Google code repository. That one is a previous version of the library. So if you go there, last night I uploaded in the project libaccent. There's a repository rewrite, and that's the current version. I think there's some mutating algorithm there, but I'm not sure which. I have not implemented sort or partition. I know that. I've been mostly concerned with find. And things where the position that I added to Andre's idea makes a real change. Um, I have implemented rotate and reverse, so you can look at that. I claim that any range is simpler to implement than any iterator for one simple reason. Equality is a binary operation. If you have type erasure and this dynamic dispatch and you have two any iterators and you want to compare them, that's annoying. Well, iterators are there. The standard library uses and provides iterators. That's one big advantage of anything that uses iterators, over anything that doesn't use iterators. My library has an adapter that takes two iterators and forms a range. It does not have an adapter that takes a range and gives you a pair of iterators. Not yet. I will write one, of course, so that it can be used in a range for loop. But as I mentioned earlier, I cannot create anything more powerful than a forward iterator with that. It's not possible. Okay, this is everything I have about iterators versus no iterators. Any questions? Yes. Go ahead.
But my main interest in the iterators is the argument in the context of distributed data structure. I would mean I want to write some sort of STL vector that and STL style algorithms that's getting the data that's on 10,000 nodes, and I want it to look just like what I would write in STL. We found this is very hard to do with iterators, and generally on distributed data structures, they just don't give you that sort of interface. Instead, they just say, you can give me some function, and I'll apply it to all of these things. And I don't know, I just perhaps was wondering if any thoughts about models or parallel iterators, ranges,
Nat, is that an answer to that, or is that a separate question?
Yeah, it's a follow-on to that. One is range versus other ranges to a sequence.
Okay. So let me sum up the question. He works with distributed systems where you have a range, some kind of element. You have elements, and you want to split up the computation over lots and lots of nodes. And what they found is that this does not work with iterators. And the question is, does it work better with ranges, or do you have any thoughts about that? The answer is no. I have not really worked with distributed systems, so I have no knowledge of the domain. And Nat said, well, what we then might want is a range adapter that kind of takes a lot of ranges and pretends that it's one contiguous thing. For the simple case, I have that range adapter. It's called concat range. It's an incredibly complicated beast of metaprogramming. It works. I'm not sure if it's applicable to that situation. Yes?
Well, I was thinking of segmented ranges. I just Matt Austin did something a long time ago. Does this make that simpler?
Do ranges as primitives make Matt Austin's idea of segmented ranges, or his paper was called segmented iterators, simpler? No. Segmented iterators or segmented ranges are exactly the same complicated or not as. It makes it maybe a little simpler because, well, now you don't get a pair of iterators back when you say give me the first segment, you get a single range object. But that's pretty much a cosmetic change. The real difficulty in the segmented iterators idea is not in the syntax. Tony.
In your case, the whole point you're trying to say is your ranges don't let you iterate them. They will iterate for you. You only pass the function, and they will apply that function to the element. You can't just iterate.
Right now, we find that's the only thing that we've done
Okay. So to sum that up, Bryce? Yes. So Bryce basically says that the model that distributed libraries right now is internal iteration. So you have a range, you give it a functor, and it calls that functor for every element. But that's a problem when you want to access multiple elements at once for some computation. And his boss basically hopes that ranges instead of iterators could provide a better interface to that. We should talk, but not now. Jeff? Or wait, David was first. Oh, is there someone I can't see? Michael, what are you doing back there? Mm-hmm. Mm-hmm. So Michael's question is essentially, well, if it's not a distributed system, if it's just different threads, does it help in that case to break up are ranges easier to break up into chunks that I can pass to threads than iterator pairs? From what I know of that kind of breaking up, I don't know the best strategies of how this chunking works. I think the interface on the syntax might be easier to understand for the user, and ranges I have the feeling that it's easier to do fine-grained capabilities with different concepts for ranges than iterator pairs. So it might be possible to develop an additional range concept that says, well, I'm not random access, but I have this function that helps break me up into chunks and say, well, that's a new range primitive. And that would be easier to insert into that than into an iterator pair. But it's not something that my library is now equipped to help you out of the box.
I just have a comment on it.
Okay.
Does your application require that the breaking up into chunks be like first three go this way, 4, 5, and 6 go this way, or is it just, can you do things with a striated iteration? Because if you could do it with a striated iteration where like the first, fourth, 7th went this way, and the second, 5th, 8th went another way, that would seem to be a pretty simple iterator adapter. A range adapter says, here's a range, give me a new range which is striated starting at the second position.
So So the comment was, well, maybe a striated iterator or a range adapter would help there, because, well, it could give 1, 5, 9 to the first thread, 2, 6, and so on to the second. Yes, probably. Of course, if that's contiguous storage, then you get a lot of false sharing if you do that. I've seen situations where someone did that kind of chunking and then instead did the proper chunking, and the performance difference was like 2 orders of magnitude because of so much false sharing. So I have one more slide, and we're almost done, so I'm going to show that slide. And if you want to go over time and ask more questions, one last slide where I compare the iterator-based range libraries. There's 2 more than I've talked to before. Chandler's library. And this library is not publicly available, but Anna Schödel talked about it on the SG9 mailing list quite a bit. I just want to give a short overview of what makes these range libraries different. So we've got boost range, where ranges are just two iterators, and all the logic is in the iterators. We've got Eric's library, where adapter ranges need to stay alive because the iterators refer back to them, and the ranges hold important logic and data for the adapters, which is an efficiency bonus, basically. You've got Chandler's ranges, where the ranges actually own the elements and therefore hold adapter logic. I have no idea how Arno's library works in that regard. Actually, I don't know whether the ranges hold adapter logic or not, because one of the arguments he brought on the mailing list was that this thing is bad. So he argued that the iterators need to still be valid once the range goes away, because of a function like that, the one that I showed on the much earlier slide, right? Because he wants that to be valid. So this shows one of the trade-offs. As I said, boost range does not document it, but all the adapters I've seen just hold the adapter iterators, and the adapter iterators hold the inner iterators by value, so the iterators are independent of the ranges, effectively. And what is the copy semantic of a range? Well, in boost range and Eric's ranges have reference semantics. You copy one range to another. They still refer to the same underlying sequence. Chandler's ranges hold their elements. You make a copy of a range. It copies the elements. And if you don't want the copy, you do moves. Arno's ranges are non-copyable. I have no idea how that works. But that's the way it is. Okay, that was my last slide. Boost range, here's the documentation. This is the first blog post Eric wrote on his library, plus on GitHub. You can find his library on GitHub. Is Chandler here? No. I have no idea where to find his library. I don't know if it's published yet. This is the documentation for D's standard library for stud range module. There's also a stud algorithm module which holds the algorithms. And here's my Google Code repository of my library. Please use the rewrite repository, not the default repository, because that thing is old and even more incomplete than my current version. On the other hand, it's stable. Okay, right, so time is over, but if you want to stay and ask more questions, have more discussion, please. Jeff.
So, after seeing your presentation,
Yes.
I would be saying Andre.
Jeff thinks Andre is correct after seeing my presentation. Did you see Andre's presentation back then?
I did.
Did he convince you?
I was pretty convinced then.
Cool. Well, so
Well, I think your position is an interesting twist on what you said, and maybe a refinement twist. Probably a good one.
okay. So Jeff said basically that he thinks my position might be a good idea. Do I think that a range is a better abstraction than an iterator? So there's two arguments where, if I understand it correctly, one hand, would everything look nicer if we used ranges as primitives? And the other is, do we need to throw iterators away? Is it historical baggage that is just hindering us? Did I get that right? So, to answer the one question, no, not everything looks nicer with ranges. A backtracking regex scanner does not look nicer with ranges. It's probably less efficient with ranges. Many things look nice, especially, so algorithm implementations, some look nicer, some look less nice. If you look at my rotate, you will find that it calls a reverse with position in addition to the simple reverse, and that's kind of weird. There might be a better way to implement it. The user code, I would argue, looks nicer. So just using algorithms looks nicer with range primitives, but it's very similar. So do I think ranges are better? I think they're a little better. And I like playing around with them. I like writing range adapters. I hate writing iterator adapters. I like writing range adapters. So yes, I prefer implementing a range library than implementing an iterator library. As a user, I have used boost range a lot, and I never had a problem with it, right? Code looks nice. I think you were first.
You mentioned with Andre's ranges, he has to work to get them allocated in registers instead of on the stack. Do you have the same problem?
I haven't done any performance measuring at all on my library so far. Still working out the concepts, the underlying concepts. I just recently said, well, my single path range concept is not as nice as it should be. I need to change it, and now I need to rewrite half my library. So I'm not where I want to do performance tests yet, but yes, I will have the same problem. And the thing is, Andre didn't work hard on his library. They worked hard on the compiler to make it possible. So I'll have to go back to Clang and do things there. But it's an ABI issue, right? So D can just define its own ABI. C++ cannot.
John, I just wanted to know why iterators were invented in the first place when SQL was written. Why did he go with iterators rather than
Why did Alex Stepanov go with iterators instead of ranges?
I would suggest reading elements of programming.
Yes, of course. So the short answer is read elements of programming. The thing is that if you read it, you find a long argument about why iterators are the right primitive. In a way, it's basically because pointers are there, and iterators are kind of a generalization of pointers. Eric. Will I be submitting a proposal? Eventually, I hope to. I don't think it will get accepted because of the backward compatibility issue, but it is an interesting talking point, and once my library is in a state where I say, well, I'm happy with that, I want to write a proposal, yes.
Can it not be made backward compatible?
I don't think so. I cannot provide anything better than a forward iterator. Because a bidirectional iterator is strictly more powerful, a pair of bidirectional iterators is strictly more powerful than a bidirectional range. Right. I'm actually, some people contacted me whether I want to participate in a paper for the range list which discusses underlying issues. I sent them my slides, so the discussion. I think